Alright, in this video we'll be going through the 2020 Waves exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you've completed the question or get stuck, unpause the video to see how I go about getting the answer. Alright, so right here we have an instrument that can be modeled as an open pipe, and the length of the pipe is 0.155 meters. On one occasion, Manu covers all the holes and plays a note that has the following displacement standing wave pattern for one of its harmonics. Which harmonic is shown in the diagram above? Alright, so for this we have an open-ended pipe, and we know that means we must have antinodes on both ends, and therefore we must have a node in the middle, and therefore we can draw our first harmonic like so, and therefore as we can see our length is equal to 1/2 of the wavelength. And so this is for our first harmonic. If we look into here, we can see we have an antinode over here, a node over here, antinode, node, antinode, node, antinode, node, antinode. Okay? In order to find each half of wavelength, we can look at successive antinodes or nodes. And so we can see we have a pair of successive antinodes right here, and so this is half a wavelength. Another successive pair right here, and so this is another half. Another successive pair right here, and so this is another half. And a final successive pair right here, so this is another half. And as you can see, we have 1, 2, 3, 4. 4 halves of a wavelength. And so therefore, as our first harmonic is 1/2 of a wavelength, 4 halves of a wavelength is going to be our fourth harmonic. Alright, there we go. Calculate the frequency of the standing wave above. Alright, so we figured out that that was our fourth harmonic, and therefore the length is equal to 4/2 wavelengths. And therefore we can simplify this to our length is equal to 2 times our wavelength, and therefore our length all over 2 is equal to our wavelength. We're given a length of 0.155 meters, so 0.155 all over 2 is equal to our wavelength, and this gives us a wavelength of 0.0775 meters. Alright, we obviously know that v is equal to f lambda, and therefore our frequency is equal to the velocity of the wave all over our wavelength. The velocity of the wave is given right here as 340 meters per second, and so therefore 340 all over 0.0775. This gives a frequency of 4,387.1 hertz. There we go. Opening and closing the holes can produce different notes. Manu opens the last hole and plays a note. The top 2 holes remain closed. Explain how the frequency of the fundamental note played with the hole open compares to the frequency of the fundamental note played with the hole closed. Alright, so when we're opening the hole, we're reducing the effective length of the pipe, okay? So effectively, we're making the pipe shorter. So if we have an open hole right here, so we have our pipe, and this is our open hole, we can effectively say that the pipe ends here, okay? However, we have a closed hole, we can say that this pipe is the length, alright? So you can see how this is the length compared to this length, okay? So effectively, when we have an open hole, the length of our pipe has decreased. And so because of that, we know our length is directly proportional to our wavelength. And so if our length decreases, therefore our wavelength must also decrease. Because v is equal to f lambda, again, the velocity of the wave is not going to change, right? The speed of sound is not going to change. If our wavelength has decreased, therefore our frequency must increase. And so the fundamental frequency or the fundamental note must increase. And you can write that in. Explain how a standing wave is produced. Alright, so we have our open-ended pipe like so. When air is blown into the pipe, obviously that's going to cause the air to vibrate, and therefore different frequencies within the pipe is going to be produced. As these travel down the pipe, they're going to be reflected upon the open end, okay? Now remember, they are reflected because these two are different mediums, okay? The air density within the pipe is different to the air density outside the pipe, so that's why reflection occurs, okay? So they're 2 different mediums. And so the wave is going to be reflected at the open end, therefore producing an antinode at this end, and the same thing will occur at this end, producing another antinode, alright? And as we know, we're going to have a node in the middle. So as the waves interfere with each other, due to the boundary conditions of us having to have antinodes on both ends, only certain wavelengths can meet these conditions. So most wavelengths do not meet these conditions and thus will not form, but the ones that do form will form fixed positions of antinodes, which are constructive interference, and fixed positions of nodes, which are destructive interference. And you can write that in. James and Tara take 2 portable speakers out on the school field and place them 1.25 meters apart. They send a signal via their computer to play a frequency of 2.5 times 10 to the 3 Hz out of the speakers at the same time. They walk along the line A to B parallel to the speakers 20 meters away, as shown below. They notice a regular series of loud and quiet spots along the line and decide to investigate the pattern. James stands along the central line and Tara stands on the first adjacent loud spot along the line. Calculate the angle that Tara makes with the central line. So we know our n lambda is equal to d sine theta, Okay, this is where n is equal to 0, and therefore this is where n is equal to 1. And so therefore we're comparing the n is equal to 0 and n is equal to 1 antinodal lines. And so we can set our n value to 1. We know our d value as that's given right here, and we're trying to find our theta value. However, we do not know our lambda value. But what we do know is that v is equal to f lambda, and therefore lambda is equal to v all over f. We are given the frequency, and we also know the speed of sound in air is 340 meters per second. And so we can simply plug in our numbers, and we get a wavelength of 0.136 meters. And so therefore we get n lambda all over d is equal to sine theta, and therefore the inverse sine of n lambda all over d is equal to our theta. Now plugging in our numbers, our n is equal to 1 times our theta of 0.136 all over our d value of 1.25 meters. And this gives a theta of 6.246 degrees. There we go. Now another method that you can use is you can use that n lambda is equal to dx over L. And as we know, tan theta is equal to x over L. Okay, and so what we can do is rearrange for x, and we get n lambda L all over d is equal to x. And therefore we can find our x value as n is equal to 1 times our wavelength of 0.136 times our L value, which is 20 meters, all over d of 1.25, and this gives an x value of 2.176 meters. Now plugging it into here, we get the inverse tan is equal to 2.176 all over our L of 20 meters, and this gives a theta of 6.21 degrees. Alright, so now as you can see, we get slightly different answers for both of them. The reason for that is because this method right here is slightly less accurate than this method right here, okay? This method is the preferable method because it's the most accurate. The reason why this method is less accurate is because this method uses what's called a small angle approximation. If you don't know what that is, I go through it in the second part of my interference videos on the Waves playlist, so you can go check that out. But if you can do this method, this is preferable as it's more accurate. The distance between A and B is 10 meters. Calculate the total number of loud spots the students could hear along this line while both speakers are producing the same frequency of 2.5 times 10 to the 3 hertz. Alright, if we go up here, we can see that this distance right here is 10 meters, okay? So therefore, if we draw that scenario over here, we have our two speakers over here, and we have A up here, and we have B down here, okay? And this is our central antinode, okay? If this distance right here, total, is 10 meters, and this is in the middle, therefore this distance right here is 5 meters, and this distance right here is 5 meters also, okay? We know that this distance right here is 20 meters because that is given up here, okay? And we also know that this distance right here is 1.25 meters because that's given right over here, okay? So now if you see, if this distance right here is 5 meters, like we just said, we can make a right angle triangle of sorts, like so, and we can find this value theta. And so therefore, the inverse tan of 5 over 20 is equal to theta. And so this gives a theta value of 14.036 degrees. Okay? Now therefore, we also know that n lambda is equal to d sine theta. Okay? Now we want to find the total number of loud spots, and so what we want to find is our n value, okay? And our n value will tell us the total number of loud spots. And so we get n is equal to d sine theta all over our wavelength. And therefore plugging in our numbers, we get our n is equal to 1.25 times sine 14.036, and that's degrees, all over our wavelength, which we found up here as 0.136, and this gives an n value of 2.229. And remember, for these types of questions, we always round down, and therefore this gives an n value of 2. Okay? And so what this means is that there will be 2 loud spots either side of the central antinodal line. And so there will be, let's say, a loud spot right here, and a loud spot right here, and a loud spot right here, and a loud spot right here, let's say, for example. And so as you can see, we have 1, 2, 3, 4, 5 loud spots in total. And so the final answer would be 5 loud spots. All right? There we go. Now it's important to know for this calculation that we can't use our small angle approximation equation where our n lambda is equal to dx over L. We cannot use this equation because that is only for small angles. And as you can see, this isn't a very small angle. It's 14 degrees. That's not very, very small. A small angle would probably be something like 0.05 degrees or 0.5 degrees, something along those lines, or 0.1 degrees, you kind of get the gist. So you can't use the small angle approximation for this calculation. James and Tara find 6 identical speakers and line them up 0.5 meters apart. They play a 2.5 times 10 to the 3 frequency, sound through all speakers. They then walk along the line A to B parallel to the speakers as before. Describe and explain the difference in the loud and quiet sound pattern they hear as they walk along the line compared to when there were only 2 sources of sound. Okay, so as a concept, this idea is basically the same as going from a double slit experiment to a diffraction grating. When we go from a double slit, right? We have a double slit, we effectively have 2 sources, right? Remember, each slit kind of acts like a source. And then when we go to a diffraction grating, we have thousands of slits and therefore thousands of effective sources of light, okay? Similar thing happened here. We went from 2 speakers to 6, so we're increasing the amount of sources. And so the same things that we observe from when we switch from a double slit to a diffraction grating occurs when we switch from 2 speakers to 6 speakers, okay? So, first one being, our D value is smaller, and therefore as n lambda is equal to d sine theta, as our D value has decreased, our theta value must increase. And so therefore our loud spots are further apart, just like in a diffraction grating where our bright spots are further apart. And so therefore, as our loud spots are further apart, there's going to be less of them between A and B, okay? Because as we remember, there were 5, okay? There were 5, okay? But then if the distance between each loud spot increases, okay, these loud spots are going to be pushed slightly further, okay? And some of them, as you can see, are going to be outside of A and B, okay? So now some of the loud spots are going to be past A and B. And so between A and B, there are going to be less loud spots. Now, don't write that there are now going to be 3 loud spots instead of 5. I'm just doing that for illustration purposes. I actually don't know what's going to occur. I haven't done the calculation, okay? We also know that the maxima are going to be more defined, and this is because as we have more sources, there is going to be more destructive interference taking place. Again, because it's more likely for the waves to be out of phase, even just slightly out of phase, than for them to be perfectly in phase. All right, so destructive interference can take place with even a small difference in the path difference, and therefore there are going to be wide regions of quiet spots. Just like when we have a diffraction grating, there's wide regions of dark spots. On the other hand, constructive interference, again, only takes place when we have a whole number of wavelengths for the path difference, okay? And because, due to the fact that destructive interference is more prevalent, these loud spots are going to be much more loud and much more defined, all right? And we can actually quantify just how much louder these loud spots are going to be. We can say that they're going to be 3 times as loud as before, okay? This is because we have 3 times more speakers, right? We have 2 speakers before and we have 6 speakers now, so that's a 3x difference, okay? So the loud spots are going to be 3 times as loud. And so you can write that all in. Explain the effect on the spacing of loud and quiet spots along the line A and B if James and Tara played a higher frequency of sound through the speakers. So, as V is equal to F lambda, as the speed of the sound wave has not changed, if the frequency increases, therefore the wavelength must decrease. And therefore, as N lambda is equal to D sine theta, if our source spacing and therefore our D value does not change, and our lambda decreases, this means that the angle between each maxima must also decrease. And so therefore, there's going to be more maxima occurring between A and B. Okay, so there'll be more loud spots between A and B. Lily and Dave are conducting an experiment to measure the frequency of sound produced by a car horn as it travels past a stationary observer. Lily drives her car from point A to point B directly past and very close to Dave, who is recording the frequency of the sound waves as shown below. Use the graph to state the frequency that Dave hears as the car travels towards him. So we can simply see right here, this is the frequency that Dave hears as the car approaches him, and as we can see, that is 900 hertz. So we can simply put 900 hertz right here. There we go. By considering the motion of the sound waves from the car horn, give reasons why Dave's meter detects a change in frequency as the car approaches him and then goes past him. Alright, so if we were to look from a top-down point of view and we model the car as a dot, okay, and we can model David as another dot right over here, okay, so this is the car C and this is David D, okay. As the car moves, it is going to catch up to previously emitted wavefronts, okay? So as the car is sounding its horn, it's producing wavefronts. but because it's moving forward, it's going to slightly catch up to the wavefronts that are in front of it. And so what this results in is that when these wavefronts reach Dave, he is going to perceive a shorter wavelength, okay? And so we can call that lambda prime, right? This is the wavelength that he perceives. And this is shorter compared to the true frequency, okay? And so because of that, we know that V is equal to F lambda, and therefore his perceived frequency is equal to the velocity of the wave divided by the perceived wavelength. Because his perceived wavelength has decreased and the velocity of the wave has not changed, he is going to perceive a higher frequency, okay, compared to the source. A higher frequency compared to the source. Then as the car is now moving away from him, right, so the car is now moved past David and now it's over here, the car is still going to catch up to previously emitted wavefronts, like so. Let me just get rid of this real quick. There we go. As you can see, the wavefronts that are facing Dave are now spread out compared to before they were bunched up. So now the wavelength that Dave perceives is now greater than the true wavelength. And so again, as V is equal to F lambda, and his perceived frequency is equal to V all over the perceived wavelength, as his perceived wavelength is greater than the true wavelength, the frequency that he perceives is going to be lower than the true frequency. And so you can write that in. Using the information on the previous page, calculate the constant speed of the car that Lily is driving. Alright, so we're able to do this using the graph provided. When Lily is approaching Dave, okay, so on approach, we know our Doppler equation is as so. Right, remember we're using a minus because we are approaching Dave. Again, if you don't know why we use a minus on approach and a plus when the car is receding, I go through that in my first video on my Doppler videos on the Waves playlist. So you can go check that out. And we know that when we are receding, our Doppler equation is as so. Okay, so now what do we know? We know the velocity of the wave because that is our sound wave and that's given up here as 340 meters per second. We know the perceived frequency on both cases. So on approach, that's 900 hertz. And when the car is receding, it's 800 hertz right there. Okay. What we're trying to find is the source velocity. Okay. So obviously we don't know that. However, what we don't know is the source frequency. Okay. But what this means is we have two unknowns and two equations. And so therefore we can use simultaneous equations. So what we can do is we can plug in our numbers. All right. So for the approach, we get 900 is equal to Fs. Again, we don't know what that is, times 340. All over 340 minus Vs. Again, we don't know what that is. For receding, we get 800 hertz is equal to our source frequency times 340 all over 340 plus Vs. So what we can do is we can multiply each equation by the denominator and we get 900 times 340 minus Vs is equal to 340 Fs. And for the receding case, we get 800 is equal to 340 plus Vs, and that's equal to 340 Fs. And as you can see, both of our equations are equal to 340 Fs. And so we can make both expressions equal to each other, and we get 900 times 340 minus Vs is equal to 800 times 340 plus Vs. And therefore we can expand. 900 times 340 is this diabolical number right here, minus 900 Vs. And that's equal to 800 times 340, and that is this diabolical number right here, plus 800 Vs. Now gathering our like terms, we get 34,000 is equal to 1,700 Vs, and therefore 34,000 all over 1,700 is equal to Vs, and this gives a source velocity of 20 meters per second. There we go. After Lily passes point B, she decides to accelerate away from Dave, who remains in the same position. Use your knowledge of the Doppler effect to explain how and why the frequency that Dave hears changes during this time. So if Lily accelerates away, obviously this means the source velocity is going to increase, okay? Because obviously acceleration is the change in frequency over time, okay? And so therefore, as our Doppler equation is equal to the source frequency times the velocity of the wave all over the velocity of the wave plus the velocity of the source, all right, using plus in this case because Lily is driving away from Dave, okay? So if our source velocity begins to increase, okay, this means that our denominator is getting larger and larger. As she keeps accelerating away, the source velocity is going to continuously increase, and therefore our denominator is going to get larger and larger. And so this means that the frequency observed by Dave is going to continuously decrease and decrease and decrease. We can also visualize this another way. If we draw the car as a point source once again, we would have our wavefronts, which she is catching up to, okay? As she goes faster and faster and faster, the gap between each wavefront is going to be larger and larger and larger. right? So the spacing between each of these spread out wavefronts is going to become larger, and so the perceived wavefront that Dave observes, right, this is Dave, is going to continuously become larger and larger and larger, and therefore as v is equal to f lambda, therefore if our lambda is continuously increasing, therefore our frequency must continuously decrease. All right, and we can also draw this on our graph, right? We had our graph right here, and it kind of looked like this. Now, if we come from over here and our velocity is going to continuously decrease, it's probably going to look something like so. And with that, we're done. See you.